So for this tutorial, we basically do a continuation of tutorial A2. That's why I also name it A2B, because it's really just the continuation, and this time we will focus on implementing some of the aspects that we saw last time on a CPU, and now we want to take a look how to implement that in a pretty easy fashion in the CTL on GPU. I think this will hold true for the projection filters, and for volume filters I have a different filter that I want to implement as well, and we will take a look into that in a second. But for the beginning, we will start with the projection filters, and setup is as usual. I have copied some of the helper functions we were using in tutorial A2, added a few more to make life pretty easy for us. We will go through them when the time comes. And in the first part of this tutorial, I want to take a look into the projection filter that we implemented in A2, and this is the masking filter operation. Probably you remember. If not, you can recall that later if you like. And so I will not display the CPU version here again, just to give you a brief idea what it was about. We just wanted to specify a rectangular region on a projection which we want to keep, and everything outside that rectangular region we overrode that we erased all the values from the projection, set them to 0, so that we end up with that rectangular masked region in the projection. And we now want to take a look how we can make a pretty simple GPU implementation in the CTL using our so-called generic OpenCL projection filter class, which more or less allows you to just write an OpenCL kernel file and then let the CTL do all the stuff that is required on the host code side to transfer data to the GPU, execute the kernel, and copy back the memory, so that your projection actually gets filtered in the same way it is also filtered when you use the CPU version that we have done last time. So to make that possible, the thing that we need to do is we need to create our kernel file, as I already mentioned, and for that I will add a new file here to my project, which I will call projection masking filter. .cl, because it will be a CL kernel file, and I add that to my project, and then we are good to go to write the kernel. And one good idea to start with is, if you want to extend something like this, it might always be a good idea to just take a look into already existing implementations and more or less just copy the things that you also need. And this is especially useful in case of filters, because you need to get the signature for the OpenCL kernel correct. And it is pretty simple to just copy one of these from the pre-existing filters. So we can go into the OpenCL submodule of the CTL and take a look in the OCL routines sub module, and what can we find in other files. And we want to look at projection filters, which can be found in processing. And then we just take one example that we can find here. Let's just take the RAM lag filter, for example, and then we can see the OpenCL kernel for that particular filter. And what I'm going to do is I will just copy the entire code that I can find in the RAM lag filter, and first of all paste it in my new projection masking filter, and then we can take a look at the individual lines of code and see what we need to get rid of and what we need to replace. So starting with the first line, this just defines the sampler object that allows us to sample values on OpenCL images. This is something we also need for our implementation. That's where we can keep it. And then we can see the filter kernel a signature for the OpenCL kernel, and this always looks the same for the first 3 arguments. These will be automatically created by this generic OpenCL object that we will take a look into in a few seconds. And this will pass to us the original projection data that we want to have filtered. Then we have an buffer object available where we need to write the result of the filtering operation. and then we get the index which projection is currently processed. So this filter kernel always processes one projection at a time, and in case we have any kind of relation of which view we are currently filtering, we get the information which one it is in this index. This is something we will not need to take care of in our filter, because we want to mask every projection exactly in the same way, no matter what view index it is. So that's not important for us at the moment, but if you were to implement a filter that requires the information which view it's currently processing, then you can make use of this third input argument here. And then afterwards, you can already see that in this comment here, we have one additional argument, and this is the way this this generic OCL filter classes work. They allow you to specify an arbitrary number of additional input arguments, which will always be passed to the kernel as individual floating point numbers. So you can pass an arbitrary number of floats to your kernel, which can then appear here in the signature. And this is the thing that we need to do for our kernel, because if you remember, when we specify our rectangular filter kernel, we need more or less 4 individual values that specify the extent of our rectangular region. And in our example from last time, we specified the upper left corner and then the width and the height of our rectangle. And in this situation here, I want to specify the top left corner and the bottom right corner. So I will use 4 floating point numbers here for my rectangle, and the first 2 is the top left corner, and the first one will be the x coordinate of the top left corner, then followed by the y coordinate, and then we continue with the bottom right corner x, and followed by y for the bottom right corner. Okay, so then we can start with writing our actual filter. We get the IDs of our of the worker that is currently processing this filter operation, and this will be always processing one individual pixel. So we get the global ID for the u and v coordinate of the current projection image that this kernel instance is processing, and this is the pixel that we need to operate on. And our operation is basically very simple, so we don't need this one here. We just need to decide, is this pixel inside our rectangle that we want to keep, or is it outside? And depending on that decision, we write the value 0 to our projection image, or we write the original value from the projection, so we keep the original value. So this is more or less all we need to do. That means we just decide whether or not the pixel is inside that region. So no need for this, and also no need for the loop, because we don't do any computation. The only thing that we need to do is we take a look if our u coordinate, that's the x coordinate on the projection, if this is smaller than our what does it need to be smaller? The top left. So if we are on the left side of our rectangle, and if we're smaller than that, we are outside. Or if our u coordinate is larger than the bottom right x coordinate, or otherwise if our v coordinates are somewhere outside. So we have this one here, or if v is larger than our bottom right y coordinate. In this situation, we want to set pixels outside direct to 0. And you can see on the bottom here, we have this write buffer f command, which is automatically available as a function inside all kernel files that you pass later on to these generic OCL filter instances that I already talked about. And these basically mimic the behavior of the typical OpenCL command, which is write image f, which allows you to write a certain pixel in an image to a value. And since we are working with a buffer here to allow the kernel to be executed on devices that don't support writable 3D images. We have this utility method that allows you to just write in a similar fashion as you would to an image, just specifying where to write, which pixel to write, and what value to write. And the last input argument here is just in order to get the dimensionality of the buffer. And it's a one-dimensional buffer, and we need to decide where to place a certain pixel. We need to know the dimensions of the image, and that's why we pass in this original projection image also to the write buffer method, but it will just read out the dimensions of this image object and nothing else. And yeah, if you would have just this here, this is exactly the same what you would do if that would be a writable image, and we would use typical OpenCL command write image f. And then we have a pixel value that we want to write, and that's it. And in case for the buffer, we additionally pass in an object, an image object that has the same dimensions as if this buffer would be a 3D image. And so we can use this exact same method here, and we want to write in new projections. This is where our result needs to go. We want to write that particular pixel, which we just created here. And there, by the way, one additional comment. The third index here would not mean this is not the projection index, so this is not which view we have, because I already said we are always processing one view at a time. The third index in this pixel would be the module index. And if we don't do any manipulations on this GenericOCL filter class, it will always pre-combine any modules that we have in the projection. So if we would have projection images consisting of multi-modules, before they are transferred to the GPU, they will be combined into one projection image. If you don't want to have this behavior, there are options to disable this, and there's I think there's quite some explanation about that in the documentation, that you can also disable the auto combine, and then you would be able in this OpenCL kernel code to also get an ID for the third dimension, and then you would know which module is currently processed and could take care of that as well. But in the regular scenario where we don't change anything at all, we always get pre-combined projections. That means they have only one single module, which is the 0th index in here. So it means we can write that pixel UV for module 0, and we are in the case where we're outside. That means we want to write the value 0.0 to our buffer, and this is just to specify the dimensions as mentioned. And then we just have the else case, which is rather simple, because in the else case all we need to do is we get the value from our old image. That means the, let's say, original pixel value, which is very simple to get with read image f. Here we can use of a regular OpenCL command, and we read from the old projections. We read the same pixel, and we only need one of the coordinates, because projections are in intensity format, where all 4 values of the float 4 that is returned by read image f have the same value anyway, so we can decide for any arbitrary component of the return value here. And yeah, if I take a look at this, I think we can entirely get rid of the image sampler altogether, I think, because we are only making use of read image f for natural numbered indexes, and in that situation we don't need a sampler, because this will always make use of the sampler that just looks up the values at their exact positions. Okay, and then we can do the same thing as here, write the buffer, but in this case we don't write value 0, but we write in the original pixel value, because this is the case where our pixel is inside the rectangle, where we just want to reuse the original values. If you remember the code from last time, this might seem a little bit more complex, and the reason for that is that last time we had this CPU implementation that manipulated projections in place, so that means we did not need to copy the old value into the result. It was already there. but the implementation for filters on the GPU is always like that it has a read-only access to the old projections, and we need to provide the result as a new output. That means we need to copy the original data into our result buffer, which was not necessary in the way the CPU implementation was provided. So that should be it. That means we have fully completed our OpenCL kernel. We can save that and then can come back to our main code. And now we just need to specify this OpenCL filter object that I already mentioned. And this is quite easy. The thing that we need for this is the location of our OpenCL kernel file we've just written. So we will have our CL file name, and one very simple way to get there is just if you're using Qt Creator, you can just click on that thing, show in Explorer, then you see where your file ends up with, and then you can just copy that and insert that here, and then you can basically get the entire path to the file already pre-assembled for you. Otherwise, I mean, it's easy to figure out where the file is, and we will discuss an alternative to that in the end of the tutorial. But what I want to have that as a standard string, because this is what is required as an input to our filter object that we will create now. So our filter in this situation will be, as I already said, one of the generic OpenCL filters, and we have one for projections and also for volumes. So it's called GenericOCLProjectionFilter in this situation because we want to filter projections. And it takes, first of all, the file name as an input, which we have already created. And then it takes a standard vector of floats with the additional input arguments, which I added to my kernel file. So if we take a look at our kernel file, maybe over here, we can see that I have these 4 additional arguments. I should also specify that here with 4 additional arguments. Just that we remember that these are our 4 additional arguments. And I can very easily just specify these 4 additional arguments here in vector of floats. And we pass in, what do we pass in? I think the values from last time should be somewhere like this. And that should already be it, because this will now, maybe I zoom in a little bit in the code here. This will now create for us this generic OpenCL projection filter object, which takes care of all the host code that is required, will execute this kernel that it finds under this file name, and it will pass along to the kernel these 4 additional input arguments. Maybe we should indicate that that's actually float, but it's not entirely necessary. Yeah. And after we've done that, we are good to go to use the filter, because this will be a filter that is usable in the exact same fashion as we had it with last time. Because if you take a look into the implementation of GenericOCLProjectionFilter, it just inherits from AbstractProjectionFilter. This is exactly the same thing that we did last time explicitly when we wrote our masking filter. We also inherited from AbstractProjectionFilter, and this is the same here. So we can use this object that is now created in the exact same manner as we are used to with our own filter that we have implemented. So we can use the filter to do something. Yeah, we could call filter on some projections, and in order to save a bit of time, I have prepared this use projection filter function that just takes as an input an abstract projection filter or a shared pointer to this, and then executes some example code for us, which we can take a look into. We have projection image with 500 pixels times 500. We allocate 10 projections, fill them with 1.0, plot them, filter them, plot them again, and then we also test some serialization. And this is interesting in this situation, because what you will see in a second is that we don't need to care at all about serialization. It's all been taken care of for us already. So we can take a look if we actually run the code, if we achieved our goal already. By the way, I should have cleared my my application output here. Okay, it takes a little bit to compile because I made some changes recently to the CTL and I did not recompile my example here. Okay, then we see we have made some mistake in the implementation of our filter kernel. What do we have? Use of undeclared identifier. Yeah, okay. So this is actually called bottom and not only bot. And then we can try that again. And we can see we wrote everything with 0. Why did we do so? Let me just check. Okay, so our original image is 1 and the final image, there are only zeros. Let me just compare what we did here. So we check whether we are outside the top left corner or the bottom right corner. And this is top left and this is bottom right. So this should be fine in general. And then we read out image value and write it to. Okay. I'm not entirely sure what I messed up here. Okay, let me quickly check if I made some mistakes. This. Ah, yeah. Okay, I see. I remembered the values from last tutorial too well because I already said that last time we actually specified the x and y coordinate of the top left corner and then the width and the height of the rectangle that we want to mask. And for some reason this time I decided to specify this corner and then the bottom right corner. And if I specify values like this, then our bottom right corner is actually not on the bottom right because this value is no, this value is smaller than this one, so this would definitely not be the bottom right corner. And if I have a rectangle that does not fit in my conventions, then of course the code will provide something stupid because we have basically everything is outside the rectangle if the rectangle has kind of a negative area then. So really specify some meaningful values here. So this is coordinate 400, 400 here. So this, if you, maybe you can see that on the bottom of the projection viewer. This is the bottom right corner and the top left corner is 100 and 300. Then we can see that our code actually is doing the proper job that it is supposed to. And what we can also see is that we get that output of difference 0 here. If you remember that from last time, this is my output that is generated by the serialization test method, which takes the filter and projection image, filters the image, and then serializes and deserializes the filter and uses this object to filter the projection image again, and then just compares the results. And we can see that both perform the same way. So serialization is already taken care of for us. And that is pretty nice, I think, because all we needed to do to get this entire filtering process running on the GPU is just writing this OpenCL kernel file. And yeah, we are already finished with the entire job of executing the masking filter operation on GPU. Okay, so we can now proceed with the volume filters, and for that we want to do a little bit of a different thing than last time. Last time we had this model application filter that operated on volumes, and we will also be using this here, but we cannot use that just right out of the box, because if you remember what we did, we had that abstract that abstract data model that told us what we need to do with our input values, and we cannot just simply pass such an object to the GPU because it just does not understand these C++ classes. And for that reason, we need to think about how we can still make use of our GPUs. And I want to narrow that down to one particular example where I want to create a segmentation filter that has some thresholds, and when a value exceeds the threshold, it will be accounted to a particular index which specifies a certain material. So we can specify a number of thresholds, and then we get an image returned back from our filter that just contains values 0, 1, 2, and 3, or whatever, denoting to which of these categories the specific voxel belongs to. And the first thing I want to demonstrate is that we can do that with our model application filter on CPU that we have written last time. And I've prepared something for that because it would be a little bit cumbersome to write our segmentation model for that. But it's pretty simple to do, and we can take a look how that looks like. But I've already written the code for that. What we basically need to do the thing that I just mentioned is that we need something like a piecewise constant model. We need a model that has a constant value for a particular range of values, so that it always returns the index of the material within that range of values in the volume. And we can inspect this model that I prepared for us. So this looks something like this. Let's go to a smaller interval. So my model only operates on the range from 0 to 1. And you can see that it's actually a piecewise constant thing for values to up until 0.2. It returns 0. Then it will return 1. And it will return the value 2 for values between 0.9 and 1.0. And this is very simply just a combination of 3 rectangular function models from the CTL, and then I just sum up these 3 rectangular function models on top of a constant model that is value 0, and then I get this piecewise constant model, which is, to be fully honest, absolutely not the most efficient way of doing something like that, but it is quite simply to do. And if you're interested in doing something like that, here's an example code on how you can just easily create such a piecewise constant model. And we can now use this piecewise constant model in our model application filter, which I copied from the last tutorial. So we have it available here as well. And we can create our filter as our model application filter. And by the way, did I actually a little bit curious, can somebody I told you last time that I will no longer be using namespace CTL, so we actually maybe I do that later on, but the code that I will finally upload to the tutorials repository will no longer be using namespace CTL. I was just amazed that I did not have that here, but I told you last time that I want to stop using that for reasons of compatibility when we add the functionality to the CTL. So our model application filter from last time takes the model that it shall apply to the object as an input. This is our segmentation model, and we need to create a shared pointer of that, because this is what my utility method, to make a shared pointer of that type. And then we can use my already prepared useVolumeFilter method to use this filter. And we can take a look what this method does. It's the same as last time. We create a volume with 100 voxels in each dimension, fill it with random values between 0 and 1, plot it, apply the filter, plot it again, and then test serialization. And hopefully this will not cause any issues, because we just used the model application filter from last time, which worked properly, and now just use it with this piecewise constant model. And If we do so, we can see that this is the result. So this is our original volume with random values between 0 and 1 more or less. And in our filtered volume, we can see that we only have 3 different values here. We have black is 0, then we have the gray voxels, which got assigned to the index of 1, and everything in this original volume that had a value above 0.9 is now assigned to value 2. So we have segmented all the voxels in our volume into 3 different categories belonging to category 0, 1, or 2, just depending on whether or not their values were in one of these 3 regimes here. And we now want to mimic this exact same thing, or not, maybe not the exact same thing, but something similar on the GPU. And we will go through 2 different examples of that. And one of it is more or less the same as this one now. And I've pre-prepared that for us because it's not much different from what we've seen for the projection filter. And this situation will be GPU version 1. And this is using a fixed number of 3 thresholds. And for that, we will do the same as before. Have our CL file name, and as you can see, I have already pre-prepared one of these filter kernels, which we will go through in a second. But for now, we just continue writing our host code here. So I do the same approach as previously. Go to the Explorer, copy the file to get the address pretty quickly, and then we can more or less copy this line here. No, I will retype it. So this is not complete. And then we can create our filter as a shared pointer to this time GenericOCLVolumeFilter, because we want to apply it to volume and not to a projection. The CL file name. And then we need to put in our arguments. And as I said, it will be a filter that is able to handle 3 different thresholds. So let's just enter 3 thresholds here. And we will be using 0.2, which I was also using in the example that you've just seen on the CPU, 0.9. And then there's an optional 3rd threshold because we only had 3 different groups, and everything above 1.0 would fall into another group, but there's nothing above 1.0 in our example. But still, I wanted to keep this with 3 thresholds here. So yeah, we cannot call that a filter here, so let's call that filter 2, very creative, and take a look into what our segmentation filter is doing. If we take a look here, we have a filter kernel with 3 additional input arguments specified here, threshold 1, 2, and 3. And then everything is very similar to before, just that now we get this input of the slice that we're currently processing. And of course, we need to somehow take care of that slice because we don't have only one slice. There's no such thing as the auto combine for slices. We don't get one big slice where all the slices are combined into one single slice. So that's why in this situation, we need to actually pay attention to this value, that this call to this filter kernel here really processes slice Z and not one of the other slices. But the rest remains exactly the same. We get the ID for the first 2 dimensions. We're processing voxel X, Y of slice number Z. So that means this, what I specified here, is the voxel that we are currently processing, X, Y, and Z. And then code is very simple. We read the original value from the volume and then just decide whether or not this value in the volume exceeds one of these thresholds. And the code is just that we assign 0. And if the value is lower than threshold 1, we will assign value 0. If not lower than that, but lower than threshold 2, we assign 1.0. And In the other case, we assign value 2, and that means if it falls between threshold 2 and threshold 3. And then we could, of course, add something on the very bottom here. If it would exceed threshold 3, we could assign value 3, for example, to it. In the implementation like it is here, it would would be left with value of 0.0 if it was bigger than threshold 3, because we do not change anything. And if we remember the model that I implemented, this step function model, this was doing the same thing. Everything above value 0.0, 0.1 was also mapped to output value 0. And then we use the write buffer method to write into our buffer. And this is, again, exactly the same as before. And I just copied the signature of this write buffer method that you don't need to provide. It's always available within these filter files. And this is taken care of automatically by the CTL. Okay, and of course you would also be fine in calculating all these things manually. You could use the buffer here and then just compute which position in that buffer you would need to write the value, but it's quite cumbersome in 3D to create a one-dimensional lookup index for 3 dimensions in that buffer, and that's why we have this utility method that does the job for you. And there's no more magic behind that than just computing the correct one-dimensional lookup. Okay, so we have then created our filter with this particular filter kernel, and then can do the same thing as before. We can use this in my prepared method here and take a look what it's doing. Maybe we don't need to get rid of the rest. Okay, so we now just need to make sure that we don't get confused. So this is our latest 2 volume viewers. I will close the previous ones, and I will also close the data. Maybe we can take a look again. This was my original data model, and you can see everything above 1.0 was mapped to 0 here as well. So that's why the OpenCL kernel is exactly reproducing the behavior of this step function model. And if we inspect the results, this is the original input, again filled with random values, and this is the segmentation result of the GPU. And you can see again that we have 3 different values here, some of with 0, 1, and 2, depending on in what of these threshold intervals the original values fell into. And what you can also see, again, different zeros, so that means the serialization test went along without any issues, because the same thing happens here. Like for the projection filter, the GenericOCLVolumeFilter takes care of any serialization things, including serializing and deserializing these 3 additional input parameters that we have here. So where there's absolutely nothing for us to do, we can just right out of the box use this along with a filter kernel that we have prepared. And basically really the only thing that we need to pay attention to is that if we specify the same number of additional input arguments here, that we also have specified in our filter kernel file. So if I have 3 additional input arguments here, then I also need to pass in 3 additional input arguments into this call to the constructor of GenericOCLVolumeFilter. Okay, and then we can already proceed with the last example that we have for today. And this is getting a little bit more complex, because we now want to have a version that can take an arbitrary amount of thresholds, that we're not limited to 3. So if at some point we decide we need 4 or 5 different materials, we can have an implementation that can take an arbitrary number. And this will take us into situation where we need to do a little bit more coding. And the reason for that is, if you take a look at this implementation, or not this one, maybe reopen it, and at this implementation, if this number of thresholds were to change, I would have to recreate a new kernel file. There's no chance that this can automatically expand this list. And for that reason, there would be only option for us, and that would be to provide thousands of kernel files for each number of input arguments, which is kind of stupid. And that's why there's a different solution to that situation. And this solution will be that we now subclass this GenericOCLVolumeFilter, do a few manipulations, and then use it as the original version was, but after a few manipulations. So for that reason, we create our own class, and I prepared a file that is called custom OCL volume filters, where we put in our class. And this file includes this generic OCL volume filter, because we now want to subclass this. And our class in that situation shall be called volume segmentation filter. And we inherit we inherit publicly, almost the same mistake again, from the generic OCL volume filter class. And what we need to do looks pretty similar to what we're already used to from other implementations. And let me just add some of the base functions. So what we need to implement is this filter method here. And we will also need to take care of serialization this time. And then what we also need is a constructor, which is this. And we will need the default constructor. We can make that private, but this time we need to implement it on our own. Oh, hell. We cannot use the default version of it. We will see in a second why. And then we have the regular constructor, and this shall take a vector containing all the thresholds that we want to have. Okay. Then we should probably also memorize these. And I think that's already it, what we need in the declaration of our class. And then we can go along with the implementation. And the first thing I think what we are going to do is we are going to write the kernel file for that, I think. So there's no right or wrong solution, but probably the most common way is that you first have your OpenCL kernel and then you write the code that runs the kernel. So we call that volume segmentation filter flexible. There's some segmentation filter.cl. And for this, what I'm going to do is I'm first of all grabbing the entire code of my non-flexible filter and put that in here. And the difference that we now have is that we don't have these additional threshold inputs here, but what we will end up with is another global memory array containing the thresholds and another input specifying the number of thresholds. And we will take care of passing these into our kernel in a second in the host code. So if we have these inputs available here, we can then modify the code. Nothing needs to be changed for the IDs because we still need to get the voxel that we're currently processing, can remain exactly the same. But after that, and why the hell is that still called compute gradient? That's the copy and paste thing. Categorize voxel, for example. And we will use the same name, same comment here. And instead of going through these three thresholds in a hard-coded manner, we will go through all the thresholds that we have in our list. So it's just a simple loop going through all the thresholds. This is smaller than the total number of thresholds that we have. Increment that. And then we check whether or not we have our reference value. So this is the value in the volume actually. If this is larger than thresholds at that particular index we're currently looking at, And if that's the case, our new value is equal to float converted of threshold plus 1. And then we should be fine. Yeah, so we are iteratively going through, and since the thresholds are always increasing, we end up with the last threshold bin, so to say, where our value is larger than that particular threshold. This will not 100% reproduce the code that we previously had, because we will not end up with a value of 0 for everything that is larger than our last threshold that we pass in. But yeah, this is some kind of compromise to get this running a little bit quicker here without too much code to need to be written. And yeah, so if we exceed threshold 0, we will assign the value of 1 to it, because then we are in bin number, in the second bin, so to say, with index 1. Yeah? And if we don't exceed any of the thresholds, we will assign value 0, because then we are in the first bin of our thresholding model. Yeah, and then if we have figured out the value that we need to write, the volume, so the category it belongs to, we can just simply write it into the output volume as we did before. So now we need to take a look at how we can get this global memory array into our kernel, and how we can pass in this unsigned integer of how many thresholds there are. And for that reason, we have this filter method here, and we will start with implementing this. And this will first of all make use of a try-catch block to allow us to figure out any OpenCL errors that we potentially introduce in our code. So we will catch any OpenCL error here, and then just write that. It's a critical message for us. And then we output the actual error message. And we also get the information about some error code, which is this one here. Okay, like that. And then we can start writing our actual code that needs to be done. And the first thing we need is we need to figure out how many thresholds we have. I always keep forgetting auto today, I don't know why. And this is to be found in our member where we stored our thresholds. We will take care of them, of the constructors, in a second. And this is just the size of this threshold, so we know how many thresholds we have. And then we can also determine the size of the buffer that we will need in order to transfer all the threshold values to the GPU. And this is simply size of one individual float times the number of thresholds we have. And then we can create buffer on the GPU and write in the thresholds. And for that, what we're doing is we create, first of all, we get, this is something that is rather important, because you need the OpenCL context that shall do the job for you, that shall handle this memory transfer. And in order to be entirely sure that you are doing this with the same context and end up in the same command queue as the execution of the filter later on itself, you should always use this private member that you have available when you do this inheritance, which is called queue. And this gives you the same command queue that the GenericOCLVolumeFilter, which we inherit from, is also using. So that means when we now pass in something to the GPU, some memory, we can make sure that the actual execution call will operate on the same command queue, such that our buffer is already transferred to the GPU before our base class tries to start the kernel on that. And for that reason, it's advised to always use this command queue that you inherit from your base class. And what I'm going to need from that is I need to get the context from this command queue. And this is called this entry in get info from the OpenCL API. So this will give us the context that the command queue that we already have is operating on. And this will now allow us to create a buffer for that particular context and then use this queue that we have here to write the buffer to the device. So the first step is we create our buffer, which is like our threshold buffer. And this will be a CL buffer, capital L. And this, as you can see in the constructor, now needs this context. So we need to decide in which context we want to add the buffer, and then we need to specify the memory flags, which are in our case, we want to have it read only. So we write in values and then the GPU shall only read these values and not manipulate them. And the size of the buffer is buffer size, which we've already computed. And then we can ask our command queue to enqueue a write buffer command of this buffer that we just created. It does not need to be blocking because we are using the same queue. So that means this will be executed before further commands that are in the queue. And then we have no offset, and the size of our buffer is buffer size. And now we need to specify the address from where we want to write our data. And this is our member where the thresholds are stored. So from this memory, we want to transfer the data into the device buffer. And that's almost it. The only thing that we now need to do is to tell the kernel that there are these two additional input arguments. So for that reason, we have this kernel member that we also inherit from our base class. This addresses the OpenCL kernel that will be executed by the by this OpenCL filter instance. And we can tell it that our arguments have changed. And if you remember, we have these three arguments that are always there. So they are taken care of by our base class. And we added these two additional inputs. So this is argument 0, 1, 2, and we added 3 and 4. So that means we set the fourth argument with index 3. And this is our threshold buffer. And then we also specify our last argument, which is the number of thresholds. And I need to, I should probably be entirely sure and static cast that into an unsigned integer, because this is what we specified in the kernel. Okay, and that's already it. We are only left with one thing to do, and this is actually executing the regular routine. So executing the regular, let's like this filter routine. And for this, we can just simply ask our base class, and we don't need this at all, and just ask our base class to run its regular filter operation on volume. So the only thing that we have done here is we have kind of introduced something like a prologue. So we did something in advance of running our filter. We created the buffer that we need. We told the GPU that there will be this buffer and this additional input. And after that, we just run the same filter operation as if we would not have interfered with that at all. We could always write code that is that does not have something like this, and it would do the exact same thing as not re-implementing the class on your own at all. So it's just calling the regular filter command from your base class and executing all the things, transferring the volume data, getting the result back, and so on and so on. And we only change the behavior, what happens before this call, and that is we create a new buffer, pass it to the device, and yeah, have the correct values in this buffer. Okay, so now we need to define our constructors. We will start with this, the default constructor. And what this needs to do is it needs to call our base class constructor. And in that case, if you remember from last time, this gets as an input the file where our filter kernel is and potential additional arguments, which we don't have. So that means the only thing that we need is we need the path to this filter file that we have just written here. And I will do the same thing all over again. Copy this, put that here, remove that. So that means it will create a generic OCL volume filter that will execute whatever is in this kernel file. And this is not sufficient for us, of course, because what we actually want to have is we want to have a constructor that can take an input of how many thresholds we want to have. And this is also very simple. We can just call our regular constructor. No, no, we actually don't need to do that, do we? I don't think we can, so let's just do the same thing. No, we can, right? So we can have this and initialize our member with thresholds. I know, I think we're not allowed to, yeah, we are not allowed to have another initialization here, so we unfortunately are forced to repeat that, or we could do it probably the other way around and relate the default constructor to that one. But yeah, we can do it like that, and probably one optimization that we can move in these thresholds here, because we need a copy anyways. That's why they are passed in by value here, because we need to memorize the thresholds anyway. Okay, so that means every time I create an object with a vector of thresholds, we will create a generic OCL volume filter that executes this kernel, memorize the thresholds, and if I call my filter method, I will create the buffer, pass it to the GPU, and then just execute the regular filtering with respect to this OpenCL volume filter that executes this kernel here. Okay, and then I mentioned that we need to take care of the serialization, but for now we just take a look at the implementation, if it actually is working properly, before we mess around with the serialization. And here we just create another filter with a very creative name of filter3. And this again is something like this, and in this situation it's called volume segmentation filter. By the way, I included this custom OCL volume filters .h already here. And then we remember we put in a vector of thresholds, and we can just straight away copy these thresholds here, which at the moment does not seem like we achieved much, but now we could use an arbitrary number of thresholds here, what we can take a look into a few seconds as well if we want. So we have done that, and then we can use this filter and see if we did everything correct. And this time I will get rid of everything here, because we have to, otherwise we have too many windows to keep track of what's going on. And if we take a look at our results, we can see that we actually have the same thing going on. We have an input volume and our output volume with 3 different values, black, gray, and white. And now we are absolutely fine to experiment with that, change these things, add some more thresholds, maybe like that, and see if that works as well. And as we can see, this is our original image. And this is the segmented one, which I must admit already has some problems to keeping track of if it's actually 5 different values. Maybe if we plot a contrast profile, we can see it's 0, 1, 2, 3, and 4. So we have segmented our object into 5 different categories. And this is now entirely flexible for us to put in any arbitrary threshold number that we want. But as you can see, difference in our serialization test is not 0, that means there's still something going on. We also get some errors here, which is most likely due to the fact that we don't deserialize the object correctly and then something goes wrong. And for that reason, we just quickly step back to our volume filter implementation and quickly go through these parameter and set parameter methods, which are quite straightforward. There's not too much that we need to do here. So parameter is, let's say, business as usual. So we have our parameter map that we will extract from our base class, convert it to a map, and then insert what we need to insert. So we insert into that our thresholds, and what I'm doing here to be a bit quicker than last time is I will use this constructor of qvariant list, which just iterates over our thresholds and creates a qvariant list. And why didn't I do that last time? Because this requires a cute version of at least 5.14, and we normally don't request users to have this end, but for the sake of speed here, I will use this constructor. It's just way quicker than just iterating over all the elements on my own and just appending them to the variant list. But you're absolutely free to do the manual approach if you're not at a Qt version higher than 5.14. And then we return it. We've inserted all our thresholds as a qvariant list and have it in our parameter object. We can continue with set parameter method, which is very similar. We start with calling set parameter of the base class. Grab the parameter map. And check if it contains our threshold values. And if so, we need to do a few things. First of all, we get the thresholds from the parameter map. Value thresholds as essencing, and we know that this is a list. And then we will do the following. We take our threshold member and resize it to the number of thresholds that have been set in this set parameter, or that are in this list. Yeah, so this is the number of thresholds that we want to set. And then we will use standard transform to iterate through the list. And we will see in a second why we cannot do the same approach as here with this iterator-based constructor, because we need to iterate over thresholds. Put the output in our member object. And what we need to do, we get a qvariant because we're iterating over a qvariant list. So we get a constant reference to our variant. And what we need to do is we need to return this variant interpreted as a float. And that's the reason why we need to use standard transform here, because we need to do something with the value. We cannot just write the values inside our vector because that takes floating point values and so on. So this is the way it goes. Writing all the thresholds that we find in this list here inside our member container that has been resized to the correct size. And that's all we need to do. And hopefully now we will see that our serialization test will also work properly and return us a difference of 0. And this is not the case. Okay, that's very interesting. Let's see what is going wrong here. I don't know. Just take a brief look again into my code. Thresholds, thresholds, thresholds. So this seems to be correct. This typo will not be the issue. um, should be like that. Let's see, we iterate over that. Maybe we can inspect what the file looks like. So we have this this function here that calls the serialization, and we should have it at temp.json. So let's see. We have a to b temp.json. Okay, and we actually get our thresholds in here correctly. The same kernel. That's really interesting. Ah, okay. Yeah, I see. I know what we messed up. We actually forgot to declare our type a new type, and it's not serializable yet. So what we ended up with, that it just fell back to the GenericOCLVolumeFilter deserialization. What's the same thing that we had before we wrote the set parameter and write parameter and read parameter thing. The only thing is that we have this the correct values in our member now, but they have not been used because the object that was created was just this one and not the correct one. So we need a new type ID. Let's do what I always recommend, getting user type here and add some value that we've definitely not used. Let's say plus 100. We've never written 100 custom classes yet. And then declare our type serializable. Declare serializable type. Volume segmentation filter. Sometimes it's the little things, but it can at times be a bit hard to memorize that you need to do these, and in some situations it will not create any errors. That makes it easy for you to figure out that this was missing. But yeah, best idea would probably be to have a checklist when it comes to serialization and just checking everything, implementing the two relevant methods, putting in a type ID for your new class and declaring it serializable in the end. And only at this point in time, you're entirely sure that it will really be serialized. And I mean, serialized it was correctly, as we have seen, but it will not be deserialized correctly until you have declared the type serializable, and if it does not have a proper unique type ID. But yeah, it's always good to see these common mistakes that happen now and then if you do something like this, because it's not very difficult to figure out what the solution is, but sometimes you just do not think about that it might be this issue. Okay, so this is all I wanted to show for today, and I hope this convinced you at least a little bit that it is really straightforward to implement operations on the GPU when it comes to filtering projections and volumes. And all these implementations can be used in any place where we have these operations in the CTL. So volume filters, for example, occur as a regularizer in the ART reconstruction. Projection filters, there's one example where they are applied, and this is within the FDK reconstruction, which can apply a customized filter on the projections if you like. And then there's absolutely all possibilities of using them all over the place where you deal with projections and volumes, making it very simple to just swap out one particular filter operation for another one at a later point in time. Yeah, okay, so I think that's all I wanted to say for this. And yeah, do you have any questions on this particular content today? And it will cause me a bit of work to get rid of the namespace CTL. Just forgot that I wanted to do that. Okay, so if you don't have questions immediately, then we can end this. No, I wanted to comment on an alternative of having the absolute file path here. So if you create a generic OCL filter object, you have two possibilities. You can either specify the entire path where the file really lives. So this needs to be the absolute path where, or it needs to be the path where the executable can really find that file. And the other option is you specify the location within or relative to the OpenCL root folder that the CTL uses. And there are two different things in that regard. One is you can figure out where this location is by using the CL file loader and asking it for the OpenCL source directory. And if we do that, we get this output here. We can copy the output and switch to that directory, and then you are in the CL source folder that is created beside your binary application, and everything that you place in here can be addressed by the CL file loader that is used internally without giving this path information again, because it knows that path already. And that means if I were to let me go in another window here. This is my tutorial folder. If I were to copy, let's say, just this OpenCL kernel from our last example here into that folder, just anywhere here, for example, then I would have the option to just, let's get rid of that another time, to that was a stupid example. No, let me do another example, because I coded that, or maybe should have planned that more properly, because I hard coded that here. So I need to go in the constructors and remove everything here. So I don't need the path any longer because the file is already in the correct location. So we could do something like that. And as you can see, it's still executing the code properly because it can find the file. Maybe it's less nice to demonstrate it on that example. I will probably put in some example for the final version where it's operating on these situations here where you specify the code exactly here. Or maybe we can do that for the final option that we also have. So this is quite easy for you to do always, because you can just query that path using the CL file loader thing. The other thing that is possible that might be even more convenient, but it needs you to interfere with your CTL installation, and this is figuring out where you have installed your CTL, and then clicking your way all the way through modules, source, the OpenCL module, and then you can find this CL source folder here, which is basically looking exactly the same like what you've just seen besides your binary. And the reason for that is that every content that is inside this folder will automatically be copied next to your binary whenever you compile a program that uses the CTL. And that means that I would have also the option to, for example, take that projection masking filter, put that in my original CTL installation, and then go on and run that example here with the projection filter, and then get rid of this entire path here altogether. And if we build the thing, then you can see that it's still working. And if we then inspect what happened, we go back to this path here. So this is the location next to your binary. Take a look here, we can see that this projection masking filter ended up being copied to that folder automatically for us. And yeah, this is probably a proper solution to put the code in the CTL folder if you have something that you know that you will be using across multiple projects that will all be using the CTL, because then you don't need to copy the CL kernel all the time next to your binary, or you also do not need to specify some absolute path on your drive that might change, for example. But it also involves like interfering with your CTL installation, which might cause issues if you at some point maybe just reinstall it or something, and then all your filter kernels are no longer there or whatever. But this option also exists, that everything that you place inside this OpenCL source code folder here will be automatically copied to any of your projects that is using the CTL within it. Yeah, so these are basically the three options that you have, copying it into the correct folder. And there might be some more options, but they get more and more artificial, so I will skip over them. These are the three most meaningful options that you have to specify the location of your CL source code file. Okay, so now we're back to potential questions. Otherwise, we are really finished with this tutorial. Okay, does not seem like there are any questions. Then thank you for your attention.